Okay, we're going to learn how to write net ionic equations, and just a reminder, before we broke up, we wrote what we called molecular equations, and a molecular equation might look something like this. So, for instance, silver nitrate, so AgNO3, that is dissolved in water, so AQ will react with magnesium iodide, so MgI2, both water soluble, and they form products. And the way we figure out the products is underneath each of the reactants we write down the two ions. And so we've got silver and we got magnesium. We know magnesium has a 2+ charge because it's in group 2 of the periodic table. So if we bring up our periodic table, hopefully you've got that little pocket one still. You can see magnesium's right here. So these guys are 1+, these guys are 2+, these guys are 3+, and these guys are 1-, 2-, and 3-. So magnesium's definitely 2+. Silver is actually one of those that you can't actually figure out from the position on the periodic table. And the way you figure it out is that you look at the other ion. So that other ion is NO3-, so that is nitrate. And you remember that nitrate has a charge of -1. So if it has a charge of -1, and you've only got one of them, then the silver must have a charge of +1. Then we go ahead and we look at the iodide. So although it says I2, that just means that that's I-. And what does the 2 tell us? Well, the 2 tells us that the charge on an I- doesn't cancel out the charge on an Mg2+. So we need a second one. So we could write the second one down if we wanted to, but there's really no need. And in a double replacement reaction, we go ahead and we basically just trade ions. So let's go ahead, and there's our silver, and it's going to trade with the iodide. So let's go ahead and grab that iodide out, and there we go. So that's the one combination. So the positive always reacts with the negative, and then we've got the Mg2+. So let's go ahead and cut that sucker out, and it's going to react with the NO3-. So we go ahead and we drag that to the other side. There we go. And we need to figure out the formulas of these. And so remember, the way we write the formulas is we basically take the charge down to the other side and ignore the plus and the minus. And of course, 1 to 1, we basically just ignore. And this case here, though, we've got 2 nitrates and we've got 1 magnesium. So we have to be a little more careful there, don't we? So let's go ahead and write the formulas above. So, oops, didn't mean to do that in green, although that is quite an impressive lime color right there. So let's go ahead and write Ag, I. And on the other side, we've got Mg, and then there's 2 NO3s. And whenever we've got a polyatomic ion, we've got more than one. Remember, we put it in parentheses and put the number down to the side. So that way it doesn't look like 32 oxygens, let's say. Okay, we got 2 more problems here. One is it's not balanced, and so we can balance that by just making sure there's the same number of ions on one side as the other. We can see immediately we got a problem because there's 2 iodides here, and there's only 1 here. So we can balance that by putting a coefficient before. Now we've introduced another problem. We've got 2 silvers and only 1 on the left-hand side, so we put a coefficient of 2 there. And then what do we have here? We got 2 nitrate ions, okay, and we got 2 nitrates. That looks pretty cool. And we got our magnesium and our magnesium, so it looks like it's balanced from here on out. So our next step's going to be to figure out which one of these on the right-hand side is soluble and which one is insoluble. So we will need our friends, the solubility rules, for that. So let's push everything up the screen and go ahead and bring on our solubility rule table. And so remember, our solubility rules basically tell us what is allowed to dissolve in water, or what things dissolve in water, I suppose. And so we look down through the rules. This is everything that dissolves, and these are the exception columns. And if it ain't on this list, we assume it ain't soluble. So here we go. Here's silver iodide. So it's got silver and it's got iodide. And if we look down the list, we see iodide. So it looks like it's soluble, but it is one of those exceptions. And so if it's got silver it is an exception. And so because it does not dissolve, then we get to go ahead and we get to write a big fat S after that. And if we like, we can put a down arrow just to show that this thing is falling down in the test tube. So awesome sauce. Okay, and there's the MgNO3 at the end. And again, if we zoom back out and we look at our solubility rules, okay, what do we see for that? Well, we've got magnesium's not mentioned on the list. Nitrate, though, is big fat soluble with no exceptions. And so since it is soluble with no exceptions, we can just zoom right in and put a little S. Oops, sorry, we don't put an S there, do we? That is not soluble. S means it is a precipitate. And so we write AQ, short for aqueous, which means it is dissolved in water. And so we have ourselves a wonderful molecular equation. So this is molecular, and this is what we learned to do before the break. So we need to go on and do a couple other things. And the next thing we're going to do is we're going to write what's called a full ionic equation. And a full ionic equation is basically the big monster cool equation here that tells us what's really going on when this thing dissolves in water. So in water, what does it mean? It means that the silver nitrate is completely dissolving and is completely falling apart and making silver and nitrate ions. And so underneath we can go ahead and we can write these out. So we're going to have Ag. So Ag. And it's a plus, and it's dissolved in water, so AgAQ. And we're going to have nitrate, so NO3 minus AQ. So notice that we are essentially splitting apart these ions. So when they're dissolved in water, then they have charges, and they are separated. And we forgot, though, because above we had a 2 in front of this, so we got to remember there's two silvers. And there's 2 nitrates, so that looks pretty good. And we do the same thing for the magnesium iodide. So it's breaking down, and it is making magnesium, so Mg, and it's got a charge. So we show that now that it is dissolved and separated, and it is also forming iodide, I minus AQ. And remember, the 2 in the formula is telling us that there are twice as many iodides as magnesiums, and so when it falls apart, we will make 2 iodide ions, something that looks wonderfully like so. And now we get to go to the other side of the screen. So I'm just going to push everything to the right because I write too large to fit it on one screen. I'm going to put the arrow in, and here is what we do. If there is a solid, those ions are completely held together and do not break apart and dissolve. So we can be extremely lazy here. We can just go ahead and write down that silver iodide and that solid. And if you like the down arrows, you can put them there. And because it is not dissolving, it is not breaking down into forming ions. And so we basically just leave it exactly as before. But the magnesium nitrate, of course, is dissolving. So we get to break it down. So it is magnesium, Mg2+. And aqueous, of course, and the nitrates. Okay, so remember the nitrate ion formula is NO3 minus. And remember that up above we have it in parentheses, and we have a 2 next to it. And that tells us that there's 2 nitrates that cancel out the charge. But when it dissolves, those nitrates go the opposite ways, right? They're negative. They don't really like to hang out next to each other. And like charges repel. So we basically write a 2 in front of there, and shows that it completely breaks down. And so let's go ahead and completely zoom out so we can fit this stuff on. And what we're going to do next is we have hit the promised land. We are ready for what they call the Nat Ionic Equation. So we're going to capitalize that because that's pretty important stuff. Net Ionic Equation, so Net Ionic Equation. And if we look above, we actually see we have been working way too hard. And I say we've been working way too hard because we've got some stuff that is on both sides. So if we look at what we have over here, that's the nitrate ion. And if we go all the way to the other side and we look over here, we've got the nitrate ion. And it really hasn't changed. And if we look at the magnesium on the left, and the magnesium on the right, you can see it is exactly the same. So it really has not changed one iota. And so because it hasn't changed at all, right, then we can go ahead and we can make a copy of this sucker and just throw it down on the line below. Okay, this is much easier done on a tablet than it is by hand. And we can say, gosh, that nitrate, right? I mean, it really didn't do anything at all. In fact, I can take my magic eraser tool, maybe, or maybe I can just cross that thing out. And I can say, that's really not doing anything at all. It is just watching the reaction. And also the magnesium, right? It's not changing. It is on the left and it is on the right, and it has not changed. In fact, we call these spectator ions because they're just like the spectator at a football game, let's say. Not that we're watching football these days, but if you were and you were cheering on the team, unfortunately, your cheers actually don't help the team at all. Don't tell anyone I said that. And so you're just really watching. And so at the end of the day, right, then we can go ahead and we can just eliminate those good old spectator ions. And so if we can eliminate those spectator ions, that gives us the final thing, the Net Ionic Equation. So we can go ahead and we can write it like this. So we got two silver ions, and they are reacting and hitting two iodide ions, and they are forming two silver iodide solids. And so we can even get lazier too, and we can say, well, that two there, and that two there, and that two there. Well, we can just divide this out, and that gives us the Net Ionic Equation. So bingo.